I'm gonna try and do this down here tonight. I might have to take you guys upstairs if the dogs start going crazy. All right. Someone tell me what to do. Oops. Hi, Michaela. Happy Sunday evening. Happy rainy Sunday evening. Until people have questions, I'm just putting random problems up. Ooh. Ah! Try that again. Angela, the answer to your question is no. They do occur in other things, but we haven't seen them yet, so you can act like right now all that happens is when we're doing hydrating of alkynes. You'll actually see it in biochemistry. The top one is a hydrogenation. That's true. What type of chemicals do I need to put in there? Jacinta, that is one possibility. Well, you put lead and carbon. It should be platinum oxide or palladium on carbon. PD, not PB. Put that answer in there. Carbon. And there we go. It's fine as long as you know which one it is. Typos are easy to fix. Okay. I'm going to give you guys another example here. It's a good day to study with all this rain. Remove my question mark. What do y'all think? Let me ask you this. Have we seen anything with benzene rings doing reactions? Not yet. They're really stable. takes different reaction conditions to get them to work. So for the alkyne with Br2, we're going to just do a regular bromination. And because there are 2 pi bonds, we can do it twice. Now, if you prefer, you can notate this a couple different ways. You can do the straight up stoichiometry style 2Br2 like that. You could also write down something like that. Both of those would be acceptable ways. You could just put the regular Br2 or, you know, be kind of understood. Jacinta, hydroboration is when we are adding BH3 to something. When we're doing it, basically a hydration via hydroboration. That's the anti-Markovnikov way to do the hydration, where the oxygen goes on the terminal carbon instead of the innermost carbon. But if you guys are thinking, bless you, Brandon. Something like that, then you would be correct. Someone asked me a question. I made boba tea, but the tea's too bitter. Can you guys hear me at all? Because you're not really saying anything. I want to make sure I'm coming through okay. Yeah, just the bromination reaction, Jacinta. The enol, it's not a transition state. You can almost think of it more like an intermediate because it is stable, but it's less stable than the keto form. So anytime you see an enol, you're going to push it towards the keto direction. Okay, so there are some exceptions to that where you can trap the enol in that form, but we haven't learned them yet, and you won't learn them until you do biochemistry. So I don't want to say it never happens, because it does, but for us, we're going to assume that it'll always go to the keto form. You could also, instead of calling it a bromination, you could just call it a halogenation. Same thing. Hi, Duncan. Welcome to the group. We're filling in question marks at this point, Duncan, but if you have any specific questions, feel free to ask. Hydroboration can't be done to cyclose. Why couldn't it? You're talking about cyclic alkanes? cycloalkanes. So yeah, you can absolutely do a hydroboration on cyclic molecules. We can't have an alkyne that is cyclic unless it's very, very large, like lots of carbons, because it can't get the 180-degree bond angles necessary in an sp hybridized bond. So sometimes you'll see molecules drawn that have a triple bond inside a ring, and then it'll just say, like, why can't this happen? And it's because of the bond angles. But you can do hydroborations in any of those. How does a hydrohalogenation? Okay, so Michaela, that's kind of a mechanism question. Let me do this. Pop. Okay. So the question was, how does a hydrohalogenation proceed using something like a sodium halide or some sort of salt, halogenated salt, and a strong acid like sulfuric acid? So let me make sure this is showing up on the feed correct. Okay. So if you have some sort of double bond, and I'll just do kind of a simple structure here, and I have two options. I have H2SO4, or I have something like HCl. Well, in any case, those are both H pluses, right? They're a proton source. So it doesn't matter if the H plus is coming from sulfuric acid or nitric acid or hydrochloric acid. It can still be used to protonate that bond. And following Markovnikov's rule, we get a carbocation intermediate that would be the most internal to the system. Now, what we have is the ability then to have some sort of nucleophile attack that carbocation to form a bond. Okay? So in the case if you used HCl, then the counter ion you would have available is Cl minus. Okay? If we used sulfuric acid, H2SO4, we would have HSO4 minus. But that's not particularly nucleophilic. It's pretty stable on its own. So what we can do is add in something like sodium chloride, which would still be a source of chloride ion, and that'll still do the same chemistry. Okay? So essentially, you're adding the same components, but in different ways. Does that make sense, Michaela? Okay, I'm looking back at the feed here. I'll go on, but Michaela, can you tell me if that makes sense? Also, I can't tell if you were showing sodium, what it looks like on the screen to me is that you drew that, but make sure that you don't draw it that way. That's wrong because that's showing there's a covalent bond between the sodium and the halogen, and there's not. It's ionic. Okay? All right, so the next question was Jacinta asking to show how to do the Oxy Mercury Ation. Yes, the halide salt is kind of like an extra step. You can look at it that way. Okay, let me... So, because we're focusing here on Chapter 9, where we have the alkynes, I will talk about how we can do it that way. So the Oxy Mercury Ation uses some sort of mercury molecule, compound, The one that your book tends to use repeatedly is mercury acetate or mercury 2 acetate. Okay. So, actually let me draw that a different way so we can see it better. There we go. Okay, so if you have some sort of mercury in there, the mercury is very electrophilic, okay? If you think about metal ions, they're usually positively charged, right? And even though this has covalent bonds attached to the mercury, you can still think of it as kind of an electrophile that's going to want things to attack it. So in this case, it's going to be one of the pi bonds, okay? So it doesn't matter which one you show it to, the one on the top or the bottom, but you're going to show that attacking the mercury. And when that happens, it's very similar to what happens when we do the bromination, where the bond breaks and puts the acetyl group is essentially a leaving group that just kind of leaves the molecule. Similarly, what will happen next is the mercury will also come in and form a bond on the innermost carbon, okay? So you kind of get these 3 arrows, and I'll number those. It would almost be easier to show it in separate steps, but the problem is that we know it acts in a concerted mechanism, meaning all that happens kind of in one step instead of stepwise. So it would be inaccurate to show it as happening stepwise. Okay. So what you end up with is some weird looking monster molecule here. Like that. And now that's going to be prone to attack by water. Now obviously at some point this is a hydration, so you knew at some point we were going to have to add in water. The water is going to attack at that innermost carbon and break that bond on the mercury. So I'm going to scroll, let me actually make this a little smaller. Can someone let me know if you guys can still see that? Can you still read that if it's that size? Oops. So I still have a double bond there. I still have my mercury. And now, oops, I'm going to show it up here. I have my water attached. Now, 75%? Okay. That doesn't want to let me go halfway. That's stupid. Okay, I'll just scroll over and then we can minimize it a little bit. Okay, so, okay, let me go back up here if you guys couldn't see it. So the alkyne reacts with the mercury acetate, right? Giving this kind of section here where we end up with mercury with a positive charge on it. It's attached to the acetyl group still, or the acetyl group, depending on where you're from. You might pronounce it different. The water's going to attack and kick the mercury off that middle carbon, and then we end up with something like this. Now, that is a really bad looking hydrogen. Let me fix that. Oops. That's a little better. Okay, and so now we have this kind of weird looking molecule that we need to do something with. So we have some base in the system. Base in this case, that looks like a G, sorry. base in this case could be more water because there's water present. It could be the acetyl group, the acetate anion basically. And anyway, those are going to be able to deprotonate the oxygen. Okay. Oh yeah, that's right. Okay. So at this point we get kind of an unusual thing. So if you notice, we basically have an enol form here, okay? We're going to have some acid in the system. Okay. And so basically this is just going to do the reaction where it converts the enol form to the keto form. So it's a good example of it doing that. So basically one of the double bonds, well, the only double bond actually, grab the hydrogen. The hydrogen oxygen can break and form the double bond on that oxygen. That's a really bad arrow, I'm sorry. There we go. Now, at this point, you essentially have done the hydration. One thing that you can do is add in a hydride source. And I don't have your book sitting on my lap. Let me look real quick. Because normally if you Google this, it'll actually show you a different mercury source. It'll usually use mercury sulfate, but I think your book keeps with the mercury acetate. Okay. I'll do it this way. So essentially, you have this reversible, right, because that's going to be in equilibrium with itself. Let me try and, I'm sorry. Maybe that will work. Okay. And so it's a little bit weird from that aspect, but if you have in some H plus in the system, some sort of acid source, and that's what you would use if you were doing this. I'll use a different color. You can actually have the electrons come down and pick up a hydrogen. Okay. And that'll give you more or less God, this is so hard to show. I'm sorry, guys. It'll work much better when I have a really big board in front of me. Okay. So you have these kind of equilibrium positions, right, between these three molecules. And in class, I didn't really go into any detail on the Oxy Mercury Ation with the alkynes. At this stage, it basically is going to break the bond to the mercury, forming the alkyne and then getting protonated again. And it kind of happens with these three structures in mind. Okay, so those three that I have there. I'm okay. Because we didn't cover the mechanism for that one, I wasn't going to do it in class. I think because it's so hard to draw this, because it's so big on this little screen, maybe I will send a copy of it to you guys, because I can do that in ChemSketch a lot easier, and send it to you guys through email, okay? I wasn't going to ask you a question on it simply because we didn't cover that mechanism in class, and it is a little bit, it deviates from the regular one with the alkenes. But yeah, I'll work on that tonight and I'll send it to you, because I'm sorry, this is just not easy to see. It's too tiny. It's far too tiny. Okay. But I will work on that and get that to you guys as soon as we get done with this tonight. Let me... What sort of things from the previous chapters will be most prevalent on the test tomorrow? I don't know. I haven't written it yet, Duncan. Assume everything. Angela, can't be done to cyclos because it adds... Oh, I see what your question was. No, it just adds to the least substituted carbon. Angela, so getting back to that hydroboration reaction you asked about, it can still add, but if I have something... I can show that one pretty easy. Hold on. So if I have a ring with a double bond and a methyl group on it, if I did the hydroboration reaction, I would get my OH out there. If I did it with the regular hydration, like the Oxy Mercury Ation, I would get it right there. So it doesn't necessarily have to be terminal, it just has to be the least substituted of the carbons, okay? If there's no difference, like they're both secondary carbons, for example, then you'd have the situation where it could go to either one, okay? And then just using that while also looking over my notes, but there's just so much. Yes, there is a lot. And guess what? It gets worse next semester. The halide solute is kind of like an extra step. Okay. So let me write down my little list of to-dos here. Send class alkyne mercuration mechanism. And for some reason, I don't understand why, getting back to the alkyne oxymercuration, it's kind of hard to even find the mechanism online. Usually, most of these types of reactions, you can, you know, easily find them. You don't have to ask me, you can just Google it. But for that one, it like misses steps. It doesn't show everything. It assumes that you can see some stuff that's not there. It's very weird. So I'd rather just send it to you so you have it for reference. But you're not going to be asked that mechanism on the exam tomorrow. Okay. I feel bad, Jacinta. Was that a bad answer? Let me know if you need more questions answered. Jacinta, the end product is just the ketone. So, Jacinta, I'll do yours, and then Lauren, I'll answer your question. But if you have something with a triple bond in it and you do the oxymercuration, you're essentially just adding a ketone to the innermost carbon that was part of the triple bond. Okay. All right, Lauren, if you have the product 2-methylpentane 3-one, so let me draw that. That's pentane, 2-methyl, pentane, 3-one. Okay. What is the starting product since that it adds anti-Markovnikov? So if we are doing some sort of hydroboration of this, that means we had to start with an alkyne, right, to get the carbonyl there. So let's look at a couple different options here. So I want you to tell me which of those molecules can exist, the one on the left or the one on the right. Yes, Heath, thank you. If you look at that here, it has 5 bonds on the carbon, right? So this one here, put an X through that. That one there's the only structure that you'd be able to use to give you that. Now, both of them are secondary carbons. So in actuality, you'd probably get a mixture of 2 products, but I only needed you to put in 1. Okay? C. Yes, si, senor. Okay, Duncan said, if you have an alkyne that undergoes bromination and chlorination, would there be 1 bromine and 1 chlorine on each carbon? Yes. So if I have let me see the question again. All right. Let's say I just have this kind of very simple alkyne, okay? Actually, let's make it even easier. Let's just do this. It's also called, like you guys could look at that and see that you would call it ethine. It's also known as acetylene gas. So if you've ever used acetylene torches or anything, that's the gas used in it. Now, something I could do in theory is to put in 1 equivalent, meaning instead of a ratio of 2 to 1, put in an equivalent of 1 to each, right? And so I would end up with something like this. Oh, you know what? Let me put in my stereochemistry there. Those add an anti to each other, right? So, okay. Oh, why is the screen not letting me go out? Equation. Yes! No, it means equivalent. And so then I can put in 1 equivalent of bromine and then basically get what you're talking about. I'm running out of room, I'm sorry. Here we go. Bromine, chlorine, chlorine, bromine, sorry. Proton and proton there. Okay. Duncan, can you confirm that that makes sense? Awesome. Okay. Next question was from Heath. Cyclopentane. Okay. I want to ask you some questions because you know the answer to this without me telling it to you. Actually, Duncan, wait a minute. I'll do Heath first. Okay. So, oh no. Hey, Brandon. Can you get me my battery charger, or my charger for my computer? If my computer dies before I get my charger, I'm sorry. I'll be back online in a second. Hold on. Thank you, dear. What the heck just happened? Oh, okay, there we go. All right. Okay, so actually, one more question. So, Duncan, it could be a meso compound if it was the RSSR enantiomer, or the meso compound would have RSSR stereochemistry, right? Those could be the possibilities, but we're not going to get in that level of detail, okay? Because you have that spinning bond, you would get it between the two carbons, you would get a mixture of the RR, the SS, and the RS likely. Okay, so don't overthink that one. Now, Heath wanted to know about, I'm going to draw this kind of big, cyclopentane. I want all of you to look at that for a second. And you say, well, I can draw it. That makes it exist, right? That's not true. What bond angles would you expect in an sp hybridized atom? I'm going to stare into the camera. And Duncan, don't try and specify stereochemistry on something like that. I mean, you could, but I wouldn't count for it. Duncan 180. Can I get a confirmation that other people agree with Duncan that you would expect 180 degree bond angles? What he said. Yes, exactly. So, are these bond angles 180 degrees? These look about more like 120 to me. So you can't have it because so the bond angles can't allow that to happen. Now, what you can have, whoops, hold on, sorry. What you can have is, let's say I had some sort of ridiculous beastly ring with a ton of carbons in it, okay? You could, at some point, get a triple bond on that, okay? I've mentioned that a lot of these type of massive rings, right, I mentioned that we can get them very large, but that they tend to react with themselves to form smaller fused ring systems. But yeah, if you have something that's really big and floppy that it can kind of move into those angles, then it could happen, but we're not really looking at those. The biggest, hi Andrew, the biggest rings that we're really looking at in our class are cyclooctanes. So that's kind of where I've cut the line on things I expect you to be able to draw and to come up with reasonable chemistry on them. Okay. Jacinta, why did the chlorine get on top? Because that's how I drew it. So this bond here that I was talking about, that one, can rotate. So with the structure I have drawn there, you don't see any stereochemistry. There's no dashed lines or wedge lines that indicate it. So because of that, you could have kind of drawn it either way. What should we focus on the most for this exam? Nomenclature, mechanisms, or identifying and working reactions? Well, you'll have a page of nomenclature, a page of reactions, a page of mechanisms, and a page of other miscellaneous information like you've had the past two exams. So all of it. You can do it. I have faith in you. Now that said, if you're like really good at nomenclature, and a lot of this class is really is really good at nomenclature, don't you frowny face me. Don't you emoticon frowny face me. Anyway, yeah, let me get my notes. So, what was I getting ready to say? Brandon just walked upstairs and the dogs got up and I lost my train of thought. I'm sorry. I was just yelling at you for frowny face emoticoning me. Now, Heath and Andrew, I think you guys came in late. Don't you, Ethan? If I could learn it, you guys can learn it. Come on. What I was going to say is, if you guys came in late, Jacinta asked me about, if you can scroll up through the feed or if you read it, she wanted to know about the mechanism for converting an alkyne to, like doing the oxymercuration on the alkynes. And I kind of ran out of room on my screen and it just kind of looked like a hot mess. So I will send you guys that. It's not a mechanism I'm holding you responsible for knowing, but it is kind of an interesting one. You can't learn and drive down the, are you watching this on the expressway? Don't do that. Sorry, I just spilled tea. I'll be right back. Whoopsie daisy. Making a mess over here. Yeah, it's not like we don't have the ability to watch YouTube after I broadcast this, Andrew. You're just being ridiculous. And see, Duncan's concerned. He needs a lab partner for next semester. And it's not like I don't have email for you to ask me questions if you have them. You came to study organic chemistry. You left criticizing Andrew on his poor life choices. Symmetrical internal alkyne, because they only form one product since they're symmetric. That's correct. Good guy, Duncan. I agree, Michaela. God, I love this class. You guys need to go outside? Okay. It doesn't matter which Heath. If it gives you the same molecule on either side, it's the same thing. And always remember, if you can name something, and it's the same name, it's the same thing, right? So I think I'm understanding what you were asking me. You were saying if I had something like that, and I added to it, which one does it go to? It'll give you the same product. So both cases, if I was doing a hydration, for example, would give me 2-butanone or butan-2-one. Same thing. Same way with the hydrohalogenations and And in reality, right, when you have things, oh look, I can use my bubble tea as an example here, right? These things are banging into each other in the reaction flask, right? So there's a perfectly good chance that both of them could form, right? That's why I showed like this plus this. But the thing is they're the same molecule. Oh, and Heath, since you asked, you know, what to focus on, you know, most of the stuff will be from Chapter 9. The mechanisms to learn or to know are the hydration ones where we used, I don't think we did the Oxy Mercury Ation one in class. Jacinta asked about it. I don't think we did we? I was just going to do the halogenation and the hydrohalogenation and then like the acid catalyzed hydration. And then the hydroboration, because it's exactly the same. And then we could name that. Yes, you can. Well, I'm hoping you can. Good Lord, I hope you can. I'm stuck on the emoji screen. Oh, goodness. All right. Oh. Well, if you did it in class, why were you asking me for it then? Don't you already have it in your notes? Okay. Hold on. Multi-step retrosynthesis. Wow. You're breaking out the big kid words. Okay. I'm going to convert back to the Kim draw screen. Hold on. Kim sketch. Let me... I don't know if you guys can even really read the live chat. Can you guys read the live chat on the screen? Is that hard to see? Because if it's there, I guess I don't even technically have to... Like, how are you guys looking at the chat screen? Because you guys respond to each other, so I know you can see it. I'm just going to say I can make my screen bigger if that's the case. Anyway, okay. So let's start off. Let's do something fun. I read the chat on my screen. Yours is too small. Oh, so you guys do have like the chat box though that you can see? Okay, awesome. Got it. Awesome, awesome. I always make sure that I say the, well, if that's the case, you know what? Yeah, I agree, Duncan. The thing is, if it's hard to see, then it's hard to see, but I can make my screen, I can make the stuff bigger by taking out the chat screen. That's why I was wondering. Gosh, Heath, give me a minute. Duncan wanted to have a multi-step synthesis problem, so hold on. Okay. So, we're going to cure cancer with this sucker. Sadly, we're not. I have no idea what I'm making. Make my bond angles not look horrible. Okay. Okay. So our retrosynthesis is going to start off with this molecule here. So that'll be down here as my starting material. And then for the product, let's try doing something. Like that. I'm gonna go let my dogs in. Give me a second. Oh, wait. I'll give you guys the arrows. And then we'll do one for you, Heath. Oh my gosh, you guys are soaked. Hey, Fiji, can you maybe wipe off the dogs? They're soaked. Thank you. I'll let you guys work on that one for a few minutes. Wait, Andrew, are you typing while you're driving? Because don't do that. Don't do that. While it's raining, don't do that. Brandon, I have a student who's like studying on the road by watching YouTube videos. The entire class is making fun of him and telling him to stop being an idiot.
Pull over? For like what?
My husband says you should pull over for a few minutes.
I mean, it's 5:53.
It is 5:53, but they keep asking me questions, so I kind of keep answering them. Okay, anyway, so hopefully you've looked at this and you have an idea. Duncan has an idea. Yeah. So a couple things we need to recognize is that we are adding a carbon-carbon bond, right? And then we're getting rid of 3 pi bonds. I'm hoping all of you are looking at that and seeing that these are things that are happening. So if so hydrogenation, nucleophilic substitution, and that we should get rid of the triple bond. Okay, so if we do a hydrogenation first to this, it would get rid of the triple bond and it would get rid of the alkene. Is that what we want? Jacinta, the one down here in the corner, whoops, that is the product, or I'm sorry, the starting material. The product is the one at the top. So when we do what's called a retrosynthesis, we use this double-sided arrow right here, or this kind of double line arrow, and that's the product that we want, and I'm telling you guys what I want you to start with. Hydrogenation of the double bond in the cyclopentane. Okay, let me ask you this, Duncan. If I put a bunch of hydrogen and catalyst in the system, is it going to know which double bond to get rid of? No. The answer is no. So we have to do the nucleophilic substitution first. Right? Okay. Just say, uh-oh. You guys are ridiculous. Okay. So, yes, exactly. So if I do my little retrosynthesis here, where I put on my double bond here, 1, 2, 3, 4, yeah, that's the same. And then sorry, give me just a second. Okay. So the chemicals that I would need to add over the bond to make that reaction happen would be some sort of base to deprotonate the terminal alkyne. So I'll just toss in some sodium hydroxide. And then we would also need a halogenated alkane. That would be, let's see, 1, 2 carbons long. Is that right? Now, it doesn't matter what the halogen is. We could use chlorine, we could use bromine, we could use iodine. I'll go ahead and use chlorine. Okay. So, I got that, and now I only need one step to get from my chemical here to the product that I want. Now we can do the hydrogenation, okay? Now we want to get rid of the triple bond, so we can't use a poisoned catalyst. We have to use a catalyst that will just destroy all of the double bonds. So there's a couple that we could use for that. Jacinta had one earlier. If you're watching this from the beginning of the video and you're like, oh, I swear we just did one of those, that's because we did. So we can do either palladium on carbon with hydrogen gas, or we could do platinum oxide, platinum 4 oxide, platinum dioxide, I'm not an inorganic chemist, sorry, and hydrogen gas. Okay, those would be our two options for that. Correct, 3 equivalents. Now if you wrote 3 equivalents, you could totally do that. That's perfectly fine. If you don't want to write down 3 equivalents, you don't have to. Okay. And then Heath wanted to know, sorry, I have to scroll back up. Well, so this would have been similar to what you could expect on the test for a multi-step synthesis problem. I usually give a little bit more the top arrow. No, the top arrow should have been showing it going towards the, oh wait a second. It wasn't the top arrow that needs to be flipped, it was the bottom arrow. Oops. There you go. Sorry about that. Yeah, they're kind of like solving puzzle pieces, right, Duncan? So that could be something. Now, usually on an exam when I give them, especially in Organic 1, I usually have some sort of, guiders, I guess. So it's not like, here's a molecule, here's 4 steps down the way, how do you get to it? I'll have like, here's a molecule, 2 steps down the way you could have this, then maybe you could do this reaction, how do you get to that? So it kind of leads you that way, because otherwise I think it's just too stressful for an exam. But that's something you would expect to see in graduate school. I don't really do that for, oh my gosh, this is killing me. Let me just do the thing. There we go. Sometimes using the Chem Sketch is easier, and sometimes this is easier. What that does. That's kind of nice. That's easy to see. Okay. All right, so let's do I got confirmation you guys can see that okay on your screen. I can see it on my screen, like on my feed, but Let me know if that's too hard to see and I'll switch back to something else. It's too light to see? Okay. Well, actually, I might be able to just do this. Can you guys see that line okay? I can see it okay on mine. Then this is a two-stepper. Tell me what the two steps are. Twinkie, stop it. What are you doing? He starts doing this weird thing when he wants people to pay attention to him. He uses his indoor voice is like ruff, ruff. And then he started tossing a toy around. Oh my gosh, this dog's killing me today. Duncan has an answer. I'll let other people say if they confirm that or not. Now here's a question. Duncan. Yes. Yes. 1,2-dihydride shift, I like it. What I want you to see, though, is that we have a triple bond. We need to get it to a double bond. So what type of hydrogenation do we have to do? We didn't specify stereochemistry here, so. Any poisoned catalyst will do. Sorry, I clicked away from my screen for a second. So I completely agree with that. So if you say, okay, well, we need to do something like adding some hydrogen gas and Lindlar's catalyst, right? Lindlar's. Alternatively, I'll write this down here. Or you could use lithium and ammonia. Right? That's another way to get a double bond in place of a triple bond. Then we would have to do the HBr. Or we could do like H2SO4 and sodium bromide. Okay, either of those would do that. So at this point, you guys know more than one way to do a lot of these, and any of them would be considered okay. All right. Now, if you want to, go ahead and name it. Now, Heath, you asked naming of alkanes and alkynes and alkenes, and your book is special. I've told you this. Real special. Trust your chem sketch. I did not go into the priority groups of 100% of functional groups because doing so would be an entire course. But if you go to the Google, and if you type in, what did I use as my search engine? Organic priority rules nomenclature. Okay. The first one that comes up on Google for me is masterorganicchemistry.com table of functional group priorities. If you click on that, you can see that there's a large table of alkanes, or different functional groups. So technically, and it goes by, if you remember, it goes by basically reactivity. Alkenes tend to be more reactive than alkynes. So alkenes get priority over alkynes. Now, that said, let me see if I can, since you guys have access to the chat box, put that in there. So if you go to that link, then that'll tell you what the priorities need to be if you're having trouble with them. Okay, now, so you could do the lithium one, or Lindlar's catalyst, that's right. We pop a spectator ion with any sort of base. I don't know what you're talking about. We didn't use any base. Do you mean halogen? Because we can use sulfuric acid. That was the second reaction we learned back at the beginning of chapter 7 or chapter 8. So look back at those. He says, what if you were to have something like 1-ethynyl 5-methyl cyclooct3ene? Well, that's a hell of a name. Hold on. Let's draw that sucker out. Oh, wait a second. Whoops. Let me try that again. Cyclooctene. 1, 2, 3, 4, 5, 6, 7, 8. Hey, that's a pretty good cyclooctene. Let's see. So we'll call that carbon 3. One ethynyl. Oops. Meaning there's an ethyne coming off of it, and then a methyl group coming off. Twinkie, stop it. Sorry. This is why I did us in our closet last time. Do you need to go outside? I'll force your little butt outside. I'm working, Twinkie. Sorry. Okay. So in this case, I would think you're supposed to number the alkene first. That's a hard one, Heath. What does ChemSketch tell us? I'm going to find out. believe it or not, I do not have 100% of all the priority rules and stuff memorized, so just the most common ones. Let's see. Yeah, so, oh, you guys can't see that, hold on. Yeah, Heath, just ignore the stupid book. I don't want to say that. Don't ignore the book, because there are some really good problems in it. But as I said, their nomenclature, they use an old style of nomenclature that is completely jacked up, that doesn't make a lick of sense to use. So, let me pull this window up so you guys can see it. So when I did this, I have 1Z, because it put in the stereochemistry for that. 7-ethynyl, 3-methyl cyclooctene. So it gave the alkene the highest priority. And then named the system in a way that would give the lowest number to everything else. Yeah, I think it's useful to have a way to check your work, and I think using ChemSketch is a good way to do that, and it uses the new system. So, hey, can you guys hold on a second? Think of a couple more questions. I'm back. Thank you. You have a problem here? Yeah, Heath, you can't get ChemSketch on your MacBook. They claim that you can, but I've never been able to get anybody to make it work. Duncan, if you go to ACD ChemSketch, like Google ACD ChemSketch, that's where you get the download for it. It's freeware. Can we do an oxidation with a base? And then one with an acid. Are you talking about a potassium permanganate oxidation? Wish you luck. I will be answering emails up until, well, I usually go to bed around 1:30. So if you guys have any more questions, you know, after this, because I'll be getting off here in a few minutes, but, you know, Heath, if after your meeting you still have some questions, feel free to shoot me an email. I'll answer them if they're before 1 a.m., 1:30 a.m. Yeah, Duncan, were you talking about potassium permanganate? Is that what you wanted? Okay. God, that is too small. You know, If you come into a test tired, you're less likely to do well than if you come in well rested. Just saying. I don't get to control your sleep schedule, but, you know. Just saying. All right, so Duncan wanted to know... The main oxidation reactions that we learned, Duncan, were the, well, here, I'll just show us. Show us an example. Okay. Being a night owl sucks. Unless you become a professor and get to make your own schedule. Because it turns out that's a pretty sweet deal. Sorry, I don't mean to rub it in your face. Okay. So, Duncan, let's look at a few different options here, and everybody who's still with me. Come on. I'll do 3 different ones. Bye! Okay. So, let's do a few different options here for oxidations. And, you know, we did reductions pretty explicitly using the hydrogenations, right? Sorry, I saw Duncan saying see ya, so I did that. Realized that it probably looked really weird with no context. So, if I have... Let's do, okay, O3. So we had the ozonolysis, right? That's an option. If you're looking in your book, it'll add in some zinc with that, and you're like, okay, got an ozonolysis reaction. If you do that, then what you need to notice is that you're basically going to cut this bond right there. That was not supposed to be 2 carbons, sorry. And so you're going to cut across that double-double bond and add in oxygens. Now, we did not learn a mechanism for it because it's kind of a hairy beast, and I didn't feel like learning it would have given us much as far as awesomeness to the class goes. So, 1/2 of it, namely this half here, let's see if you guys can, okay, I didn't know if it could see, you guys could see the highlighting or not. So that half will give us basically ethanol, also known as acetaldehyde, and then the other half will give us that. So acetone. Okay, so that's one option. That's a type of oxidation. Most people don't call that an oxidation, they just call it an ozonolysis, but it is a type of oxidation. Okay. We also learned how to do reactions using osmium tetroxide, so OSO4. And I said if you see OSO4, you're going to do a reaction where you're basically going to be putting in alcohols across the double bond. Okay. So what it would look like then is this. Once again, didn't learn a mechanism for it, but you get the dihydroxylated product. Okay. There's another reaction that we learned that will give you literally the same exact thing. So I'm going to put that underneath this arrow because it'll do the same thing. So I'll say, or you can use KMnO4 along with sodium hydroxide, or some sort of basic condition. Now, the way that I remember this, and Duncan, I know you have your funny little mnemonic devices that you use. So look at this and say, it has an OH minus on it. These have OHs on them. Okay? So if you're using it in the basic conditions where you're using OH minus, think of it as giving you OHs on there. Okay? If you're looking at the potassium permanganate. The other one that we learned is if you're using potassium permanganate under acidic conditions. Once again, did not learn the mechanism. There we go. And so that one is the one that I said it kind of depends on what's connected to the carbons that make up the alkene. Okay? So if it's a terminal alkene, you end up getting carbon dioxide and some sort of carbonyl group on the other carbon. In this case, because it's kind of an internal group, you would end up getting this. So you'd get a carboxylic acid, and then a ketone. Now, this part, this part here that I'm moving around is this part here. So in some ways, it's almost like the ozonolysis, where it replaces the double bond with a ketone or some sort of carbonyl group. And then anywhere where there's a hydrogen, you get an OH. If it's a hydrogen directly connected to the carbon. That I have, I think, lined out pretty well in the online problem set for Chapter 8. It's at the bottom of that document. I have some different examples of what happens if you do that. But these are essentially the 4 different ways we've learned to do oxidations of alkenes. We did not really show how to do oxidation of alkynes other than doing a hydration reaction. These reaction conditions that I have here, you could work with alkynes if you did the hydrogenation first to get the alkene. So if you used a poison catalyst to take it down to the alkene, then you could do any of these structures. Okay? I hope that makes sense. So one will be an aldehyde and the other will be a ketone. Oh, for the ozonolysis? Yeah, I mean, it just depends what's connected there. So because there's a hydrogen already on here, whoops. Oh, come on, why won't you let me? I see. My bad. Here we go. So because there's already a hydrogen there, it's going to basically be the same, the same hydrogen right there. So it doesn't really do anything except place in oxygens where there was a double bond. Whereas with the potassium permanganate, it's a little bit different. It doesn't use the same mechanism. Okay? Who else still with me? Jacinta, are you still here? Michaela? Who else was here? Duncan's the only one asking me questions now. It's just you and I, Duncan. Okay. I think I'm going to go ahead and hop off. We've been on here an hour and a half. I'll let you guys go study. Jacinta, if you're still listening, I'm going to post... Hi! Hi, Michaela. I'm going to go ahead and post... Sorry, I'm reading what you just wrote, Duncan. That's right. Yeah. So here's one hydrogen right there. And it goes to make the carboxylic acid. I was going to say though is, yeah, I'm going to go ahead and head off. I'm going to post for Jacinta. I think I'll just write it out and take a picture and send it to you guys. It's fastest that way. So you can get a copy of the Oxy Mercury Ation mechanism for an alkyne, which does differ a little bit from an alkene. Somebody came to me the other day in class and got a copy, in my office, but I think, yeah, it was Alicia. She's not on here tonight, I don't think. If she is, she's being quiet. So, you're welcome, Duncan. I will talk to you guys later. Once again, I'll be up until at least 1:30. If you have questions, hit me up. Just take pictures, email me, whatever. I get Facebook Messenger notifications on my phone as well, so I'll know if you're trying to get in touch with me. I'm getting ready to go write the exam. I'm going to drink my boba tea, and I'll talk to you guys later, okay? I'll see you in the morning. Super early in the morning at 11:15.